Hello, everyone, and welcome. Today we've got a fantastic UCSI University School of Engineering explainer. This was proudly prepared by Associate Professor Dr. Ramani Bai and lecturer Mr. Taha Mohammed Jassim right here at UCSI University Kuala Lumpur. I'm going to be your virtual lecturer today, and we are diving headfirst into a really critical problem for all you civil, mechanical, and industry engineering students out there: concrete workability. We are going to master these concepts step by step for real-world industrial scenarios. All right, let's just jump straight into this real-world diagnostic tool. What you're seeing here is a live slump test in action. Throughout this explainer, we're going to see exactly how this simple little cone of wet concrete actually prevents catastrophic structural failures long before a single wall is ever poured on a job site. Pretty cool, right? Okay, here's our roadmap for today's tutorial. We're looking at why workability matters, the slump test step-by-step, slump math and an exam summary, the compacting factor test steps, factor math and its exam summary, and finally, real-world engineering applications. We've got quizzes packed in here too to make absolutely sure you ace those final exams and are fully prepared for modern industrial maintenance. Section 1, Why Concrete Workability Matters. Let's look at the foundational challenges. So, first things first, we define workability not as the final compressive strength of the cured concrete, but really as the fluidity and cohesiveness of the fresh, wet mix. It's basically a measure of how easily that concrete can be mixed, placed, and compacted without the heavy aggregates separating from the water and cement paste. When that separation happens, we call it segregation, and trust me, we do not want that. The consequences of getting this wrong are honestly pretty severe. If your mix is too dry, well, it resists flow. This leads to really poor compaction, leaving behind these dangerous voids and a structural defect we call honeycombing. But on the flip side, if your mix is way too wet, it results in excessive bleeding. That's where the water just rises to the top, leaving you with severely weakened concrete. So our main objective? Verify that consistency right there in the field to prevent some wildly expensive construction errors. Moving on to Section 2, Slump Test, step by step. Let's walk through this field method. Okay, let's step into the lab setup. Step 1, we thoroughly clean the inside of our slump cone, dampen it just a bit, and place it on a rigid horizontal metal plate. Step 2, we fill that cone in exactly 4 approximately equal layers. Now, Step 3 is absolutely vital, especially for your exams. Each layer has to be tamped with exactly 25 strokes, using the rounded end of a tamping rod. You want to make sure you're distributing that downward force evenly across the whole cross-section. Once it's full, Step 4 is to level off the surface with a trowel. Now here's where your basic statics principles come in for Step 5. You've got to list the mold slowly and purely vertically, no twisting allowed. And you have to do this whole process within exactly 6 minutes of adding the mixing water so the concrete doesn't start setting up on you prematurely. Finally, Step 6, we immediately measure the difference between the top height of the mold and the highest point of that subsided concrete to the nearest 5 millimeters. You will definitely want to memorize this table for your exams. When you lift the cone, gravity takes over. A true slump subsides uniformly and mostly keeps its shape. That's a valid test result. A shear slump is where one side just kind of slides away. That tells us it lacks cohesion. The internal shear forces were just too great, and you've got to retest. A collapse means, you guessed it, the mix is far too wet. And a zero slump? That's when it just sits there, retaining its shape completely, meaning you've got a very stiff, extremely low workability mix on your hands. All right, Section 3, Slump Math and Exam Summary. Let's do some calculating. Grab your calculators, everyone. Here's our first problem-solving quiz. If the original height of your testing cone is exactly 300 millimeters, and after lifting the mold, the highest point of your slumped concrete is sitting at 220 millimeters, what is the reported slump value? Think about it for a second. And the answer is 80 millimeters. It's super simple. We just subtract the slumped concrete height, which is 220 millimeters, from the cone's original height of 300 millimeters. This 80 millimeter true slump tells us we have a medium workability mix, which is honestly perfectly balanced for general construction work. Real quick, before we move on, let's lock in these slump test limitations for your finals. First, human subjectivity. Variations in how you manually tamp or visually measure can totally skew your results. Then there are environmental factors. Things like high heat or wind can dry out the mix way too early. But the biggest limitation, it just flat out fails to accurately measure highly fluid mixes, or those very dry, stiff mixes. So, what happens when the slump test fails us? Let's say you're an industrial engineer building a highway or a massive foundation. You actually need highly stiff, low workability concrete. If you did a slump test on that, you just get a zero slump, which gives us literally zero useful data. For those stiff mixes, we have to pivot and use the compacting factor test. Which brings us to section 4, compacting factor test steps. Let's look at this gravity-based lab test. Okay, so the apparatus for this one is pretty neat. It's 2 conical hoppers stacked right above a cylindrical container. Step 1, you gently fill the upper hopper. Step 2 relies heavily on basic statics and dynamics. We open the trapdoors and just let gravity pull that concrete down through the hoppers and into the bottom cylinder. For step 3, we cut the excess off the top and weigh that cylinder. This number right here gives us our partially compacted mass. All right, phase 2. Step 4, we completely empty that cylinder out and refill it with concrete from the exact same sample. But for step 5, this time we manually compact the concrete in 6 equal layers using a heavy compacting bar. We are meticulously tamping it down to force out all those microscopic voids. Then, step 6, we weigh the cylinder again. Because it's packed much tighter, this heavier measurement gives us our fully compacted mass. On to section 5, factor math and exam summary. Let's calculate this factor. Time for our next knowledge check. Let's say, in our lab experiment, the partially compacted concrete, the stuff that just fell in via gravity, weighed 9.4 kilograms. After emptying it and manually compacting the same mix with our tamping rod, it weighed 11.6 kilograms. So how do we calculate the compacting factor? I'll give you a second. The answer is 0.81. All you do is divide the partially compacted weight by the fully compacted weight. It's a really crucial concept to grasp that a compacting factor closer to 1.0 means you have a highly workable fluid mix. A lower factor, like our 0.81 here, signifies a stiffer mix, perfectly demonstrating that it naturally resists easy compaction. Keep these compacting factor limitations in mind for your exam summary. While it is way more precise than a slump test, it's not perfect. Concrete can actually stick to those metal hoppers because of friction, which means you have to subjectively push it down manually. You've also got to remember the reality gap. The pure gravity drop we use in the lab might not perfectly mimic the massive heavy mechanical vibrators they use out on an actual construction site. Finally, section 6, real-world engineering applications. Let's tie this all back to the industrial site. Out in the real world, slump testing is what ensures your standard concrete flows easily around all that steel rebar in your everyday walls and columns. But when you are dealing with really complex industrial precast elements or heavy highway pavements, the compacting factor test is what guarantees your stiff mix will actually hit the required density. Both of these tests are absolutely essential. They give engineers the immediate data they need to tweak that water-cement ratio on the fly, making sure no dangerous voids form in those highly congested reinforcement zones. I'm going to leave you with this final puzzle to ponder for your exams. Let's say your on-site slump test suddenly reveals a total collapse slump, meaning it's way too wet, but your industrial project explicitly requires a stiff, durable mix for heavy highway paving. How are you going to adjust your water-to-cement ratio and your aggregate proportions to engineer a safer, stiffer mix? Think back on all the principles of workability we just covered. Thank you so much for joining this USCI University Explainer, and hey, happy studying!